By the end of this upcoming module, you should be able to do the following. Define cryptography and other associated terms. Explain what and how cryptographic mechanisms solve different problems. Discuss how cryptographic mechanisms work. Some examples are ciphers, encryption, digital signature, and hashing. Contrast the different cryptographic mechanisms, such as symmetric versus asymmetric, and stream versus block ciphers. List examples of cryptographic mechanisms, such as the different types of algorithms and ciphers. Describe a public key infrastructure, PKI, including its purpose, and list the main PKI components and describe what each component does. This module will give you a good foundation in cryptography and PKI. Cryptography is the study of writing or solving codes. This straightforward definition belies the complexity of cryptography and the challenges of implementing it on a computer network. Public key infrastructure, PKI, is the name of that implementation. Simply speaking, PKI is an infrastructure composed of hardware, software, policies, and procedures that facilitates the management of public digital keys and makes cryptography over a network and the internet possible. If you have ever connected to a secure website using a web browser to bank or to make a purchase, you have used cryptography. Cryptography is ubiquitous in the modern landscape of communications and commerce. It is also simple to use, yet the technology, hardware, and software that make network cryptography possible is anything but simple. Although network cryptography is complex, it has been made simple to use for you and me. This module explores the world of cryptography, including the various technologies, concepts, and components that permit its implementation on a computer network. Like your experience connecting to a secure website, this module endeavors to make the complexity of cryptography simple. Cryptographic technology allows you to encrypt data and sign data digitally. Encryption is the process of converting plain text to cryptotext. In other words, making something that was readable unreadable. A digital signature also uses cryptography to produce a unique value that can be tied to a person. In most jurisdictions, a digital signature is legally equivalent to a handwritten signature. Encryption and using a digital signature satisfy a number of objectives. For example, encryption ensures that information remains private and confidential. A digital signature guarantees the integrity and authenticity of the data. It can be used to identify or authenticate an entity. It can also ensure non-repudiation. Non-repudiation has legal implications and means that the signee cannot deny having signed the information. If the information is a legal contract, the signee is bound to the contract because of their digital signature. By satisfying these four terms, confidentiality, data integrity, authentication, and non-repudiation, cryptography has facilitated the rise of e-commerce and secure communications. In this module, you'll learn about ciphers, digital keys and certificates, cryptographic algorithms, hashing functions, the digital signature and encryption processes, and PKI. After you complete this module, you'll have a stronger grasp of how these technologies work, and you'll have a keener insight about how they have made e-commerce and secure communications possible.